Hi everybody, welcome back. What I want to look at here now is this example that we'd started on in the last video where we had a vector OA defined as 3i plus 5j, or if you prefer just 3, 5, and we had a vector OB defined as 6i plus 1j, or if you prefer just 6 comma 1 in square brackets. So the third thing then, once we got those two vectors, is to say, well, what would you do to add those two vectors? And we know that in geometric vectors, if there was no Cartesian plane, we would just take one of the vectors, say vector A, right? We would just take vector A, and we would move it over, take an equivalent vector to vector A, and add it to the head of vector B, and then you get tip to tail or head to tail addition of vectors, and you get the result, okay? But we're going to look at it algebraically, because algebraically seems to be the preferred method when you deal with XY axis. So if I want to figure out what OA plus OB is, what I can do is I can do this in one of two ways. I can simply take the x components of vector OA and OB and say that that's going to equal to x1 plus x2, all right, which are the head positions of those two position vectors. And then I can take the y components of the vector OA and OB, which is 5, or y1 plus y2, I should say, right? Okay, so y1 plus y2, see if we can get that to undo. And right, that will give us our sum vector. So what we have is we have 3 plus 6 comma 5 plus 1, and that is equal to 9 comma 6, and that is the resultant vector. Okay, that is the resultant vector that you would get by adding vector OA and OB. And I think, as I might have said in a previous video, this vector that I've drawn here is the actual incorrect vector. It should go to right here. Okay, that is your resultant vector right there. So there's been a slight technical error in terms of the output y value for the vector OA plus OB. The correct position vector would be 9, 6, because the y components of OA and OB are 1 and 5 respectively, which add to 6. And if you look at the vector here, its y component is 7, so it's too much. Now the other way that you could add these vectors would just be using the standard basis vectors. You could say that OA plus OB is actually equal to 3i plus 6i, comma, 5j plus 1j. Now we wouldn't actually even put the comma there, we'd put a plus, because we're just treating them almost as if they're algebraic expressions, using I and j as the standard basis unit vectors for the x and y direction. So what we end up with is OA plus OB equaling to 9i plus 6j, and that is exactly the same as the vectors written in what we call component form. So when you have it written in square brackets as 9 comma 6, that's what's called component form. And we also have the vector written in standard basis form, which is 9i plus 6j. So that's how we would add the vectors. And you can do that for any two vectors that are located on the Cartesian plane. And if you take a look at our diagram, obviously 9i plus 6j, since we have it at the origin and going to that point, we could say it's a position vector. But once again, you can take that position vector and start it anywhere and draw an equivalent vector that has the same components. Okay. Now, the last thing we want to talk about is scalar multiplication with vectors in a XY axis scenario. So what we want to do is we want to look at, for example, 4 here. Well, 4 is saying to us, if you had a vector that was defined as negative 5, 6, you could call it vector A, was equal to negative 5, comma 6. Well, you could, if you wanted to, multiply that vector by a scalar, and the scalar in this case being 4, and you could just say 4 times vector A would actually equal 4 times negative 5, comma 6. And the result of that would be a new vector that goes in the exact same direction, but is 4 times as long. So that would equal negative 20, comma 24. And that would be a vector that is same direction, but of greater magnitude than the original vector. Okay, and if you were going to do that same process using the standard basis units, you could just do this. You could do 4 bracket negative 5i plus 6j, and then you could just distribute the 4 in. And since I'm running out a little bit of space here, what I'll do is I'll move up and I'll say what you'd get is you'd get negative 20i plus 24j. And that would be an equivalent vector written with the standard basis unit vectors, okay? So this and this mean the same thing. They're just written in a slightly different form.